My name is Bob New. I've been a software engineer for many years. I graduated from this program in 2009. A couple years ago, I had a fantastic opportunity. I quit working. What I mean is I went to work for myself. My wife and I lived off of our savings, and I worked full time on this project. The original idea was to find something to write a paper on, and then publish the paper, and then go back to work after that point. However, what I discovered was, to me, much more exciting, much more valuable, and so I've just continued to work on that. Now, reality has set in, I've had to go back to work, but I'm still very excited about this project, and that's what I'm here to talk about. So I'm going to talk about traditional ways of representing tree structures and for traditional ways of building tree structures. And then I'm going to compare that with this thing I've created called simple links. Simple links are a way of creating trees that you'll find is different from the bottom-up way of creating trees. Then the whole reason why I went into this was because I was trying to figure out how to improve parsing overall. If you've worked with parsing, you understand that it can be a very slow process compared to what we would expect from a computer. And in fact, I've come up with a way that is, I think, is very fast and very useful. So I'll talk a little bit about what it means to parse, and I'll show some experimental results that I have. And then finally, if there's time, I will do a little bit of speculation about what this thing does and talk about how it might affect our ideas about linguistics. So here's a typical tree. This is a tree that for this sentence. Well, I'm not going to talk about the specifics of the nodes themselves. So, for instance, this node here and these nodes up here, the horizontal lines represent nodes. And typically you see, or frequently you see these trees drawn with the lines coming together in a point. And I have not drawn them that way because I found that for simple links that it's easier to understand how they work with the horizontal lines spread out like this. However, except for what I just said, I'm not going to go into specifics of trees. Every theory has their own specifics about how trees should be made, and to me that's not interesting. What's more interesting is the bigger picture. Okay, so with a bottom-up parser, when you're parsing this sentence, you start by putting leaves on some or all of the words, and then you build branches on top of those leaves. So here we see these branches. I see these use my mouse.
Yeah, and you'll have to fix that way more, otherwise we're not going to hear you online.
Right. So here, this branch here, and these branches have been built on top of the words of the sentence. And you'll see that these branches, they're incorrect. The first branch here, Stevenson makes, the branch in the final tree has to include all of Stewart and Stevenson. So this branch is incorrect. The branch next to that, equipment powered, it sort of ends up in the final tree, but the label on the branch is incorrect. So my point is that when a typical parser using bottom-up does all these things, it has to try all of these different combinations. And it goes, there's thousands, literally, for this sentence, there's literally thousands of combinations that it has to try. And that's what makes the parsing process so very slow. So much of the research that you read today is about creating heuristics, creating ways of getting around that problem of having to try so many different branches. So while I was here at the UW, I found this paper by Yoav Sejner. He describes a process of parsing sentences that it is very similar to what I've come up with. This was the jumping off point for me. He builds these trees from left to right. So you start with the second word of the sentence here, no, and you move to, you create links from that word, and then you go on to the next word, and you create links from that word, and you go on to the next word, and you create links from that word. So each word, starting with the second word on, has one or more links that go to words that come before it. These links have arrowheads, so you see, for instance, the link between the and no. It is pointing to the, but the link itself was created when we're on the word the. So it's actually a link that's going back. the arrowhead gives you the direction for the link, but it's created at the time that you're on the word on the right.
And you actually had a content question coming from Spencer saying, how do you decide which word to start on? Somehow identify ahead of the predicate.
Okay, so in this process, there are no heads. All there are is attachments. So what I'm going to go through now is showing how Simple Links creates this tree. We start with the second word, and we link from and to Stuart. We're on and we have to link to a word that comes before. There's only one choice. There are choices as to the shape of the link, and on a later slide I'll talk about the shapes. But in this case, so we're linking from and to Stuart. Then we move on to Stevenson. It is, in this case, is going to link to Stuart as well. So again, so you get a sense of that this is just a left to right process. So I was talking about these words. Makes is linked to Stevenson, linked to Stuart. The shape of this branch is different than the first two branches. And like I said, I'm going to talk a little bit later about how the shapes get created. We go on to equipment. Equipment is linked to makes. So the shape of this branch says that equipment is below the node for makes. So what I'm trying to show you here is that you can get a sense of the fact that it's left to right. We start at the left, we work one word at a time. For each word we have to decide where it's going to link to, and we're going to have to decide on the shape of the link. So to create the shape of the link, we use these 4 link actions. At one time I had 18 link actions, but I whittled it down to these 4. And in fact, I believe we could do it with 3 of these link actions, but for today I'm going to stick with 4. The first link action is the simplest, append. What it means is find the node of the target word. So Stuart is the target word. We're finding the node for that, and we're attaching the word to that same node. This blue line here represents the node where we're attaching the word and. For an insert below action, the action means find the node of the target word. Here, the target word for equipment is makes. The node for makes is this horizontal line up here. We're attaching a new node below the target word. That's what insert below means. And then we're attaching equipment to that new node. See how that works? Insert above is very similar. The target word for diesel is and we find the node above diesel. We create a new node above that node, and then we attach our source word to that new node. And finally, insert above and below. This is one of the actions that's used most often. For this one, we create 2 new nodes. We create a new node above the node of the target word, and then below that node we create a new node, and we attach the word to the second node that we created. So here the target word is Stuart, the source word is makes, the target word is Stuart. We find the node for Stuart. We attach the node above that. We attach a new node above that, and then we attach a second new node below that first new node, and then we attach makes to that word, or excuse me, to that new node. So what I'm trying to question.
I'm sure you'll get to it. I was just wondering, how do you select that new upper node as a target for future? Like, looks like all of your nodes so far have been one-to-one identified with single words.
So the node that contained Stuart was this node, and because of the link actions, because this one is also linked to it, it's above it, it's above this node. Now if we wanted to link to Stuart again, we would link to this node. So if there's an append to Stuart that comes later, it would start with that new node. That's a good question, thank you.
So just to rephrase that so I understand, what you're saying is that when you link to a node, you actually link to the highest node above a word. So if you're linking to Stuart, you link to the highest node above Stuart.
The highest node above a word, I believe that's true, but I wouldn't.
Okay.
Yeah, you have to go, you find the target word, you going up so that you're staying left essentially.
Okay,
There
yes,
may be a
so-
node that's higher than that, than the one that's actually coming to, but you have to make sure that it actually leads down to your target word.
So
essentially.
if we were now to take equipment and try to link to and,
So, okay, that brings up one of the rules. You can't link to a word that's inside a node like that.
the only accessible thing to link equipment to would be either makes or Stewart.
Yes, that's a very good way to put that.
I'm sorry, I think I kind of I missed something. Why are you referring to Stewart and not the Stewart?
Okay, so the question is why is makes linking to Stewart and instead of to Stewart and Stevenson? What happens here is that we're creating links between words in the tree, and the underlying process says find the target word and the source word and do these things that I've been describing for creating the branches. So then above that you put a decision process that says, and I'm going to get to this, that says should I attach here or should I not there? And it's at that point you can either treat it as a single word or you can treat it as a node that's a phrase of some sort. Okay? Okay, so this claim here, I put it in a paper, I submitted it, and one of my reviewers flat out did not believe what I was saying. I was astounded that he didn't believe me because I didn't bother to put it in the paper that I've done this. This works for any tree in the Penn Tree Bank. I've gone through and converted all the trees to symbol links and then converted them back to trees and then look for differences between the two trees. And the process works for any of the trees in the Penn Tree Bank.
How do you handle unary nodes?
Internal non-branching nodes. Okay, so if you need an internal non-branching node, then you have to add another field to the simple link structure. If you're not doing internal non-branching nodes, then you can handle with just two fields, the target word and the link action. If you want to do internal non-branching nodes, add a third field. And I've done the same test with those trees as well, and it works. So you can, basically you just count the number of nodes at the time that you're doing the attachment.
So when you say you get back the original Penn Tree Bank trees, it's a non-lossy conversion.
Yes.
What about the node labels?
Okay, so it just does the structure. It loses the node labels in that process. So you can add a field or multiple fields so that when you take the tree, you convert it to the array of simple links. If you add more fields to each of those simple links, then you can do a non-lossy conversion to go back, recreate the labels for the nodes. Except for the very first node, because the very first node comes from the first word, and there is no link for the first word, so you have to do something funny there as well. But it can be done, I have done that. For the stuff that I've done, I've found that it's not necessary to work with the node label names.
This may be a really ignorant question, but I'm okay because I want to understand it better. Can you explain how this is different from a C parser that just converts back into the phrase structure?
Right, so dependency parsers don't create constituent trees. They create dependency trees.
You can
do a conversion back and forth, but the conversions are not exact.
Okay.
Okay, so
this
this
is an exact.
This is creating a constituent tree as opposed to a dependency tree. So
that
yeah.
is exact to what?
Yes. Yes, exactly. So I didn't repeat the question. He was asking about dependency parsers versus constituent parsers. Okay, so I talked about the empirical proof, converting all the trees in the Penn Tree Bank. There is a mathematical proof. I'm not going to talk about it today, other than just to say there are two halves to it. First, you have to show that all of the nodes of the tree can be created at the time they need to be recreated, and that has to do with the link actions. And then the second half is to show that each of the words can be attached to the node where they need to be created, attached to. And it's a relatively simple proof. I'm hoping I haven't finished it. So you'll see down here at the bottom of the slide the link actions for each of the words in the sentence. And as I was going through it, you got a sense of where the target words for each of the words was.
Sorry, did you just say it's a relatively simple proof but you haven't finished it?
That's right.
Sorry, I want to make sure I heard right.
Okay, so now, what if we're trying to parse? Everything I've done up until spoken about so far has just been recreating the trees. What if we're trying to parse? What if we don't know what the tree is supposed to be? So the way it works is you get to a word of the sentence, and all you have to do is decide the target word and the link action. You just have to pick those two things. It's a very simple decision to make. Once you've made those decisions, then you just create the branches the way I've just already described. So the process of deciding which word with should be attached to. It can be attached to powered, it can be attached to equipment, it can be attached to makes, and it can be attached to steward. That process of deciding, it can be a discrete process, discrete logic, or it can be a stochastic process, or it can be some mixture. And I've done all three of those so far. What I'm hoping is that I can send a spark here, and somebody here would be interested in putting a unification decision on top of this. It's not HPSG because it's not head-driven, but it is something like that. And if not, I'm going to get to it eventually. It's just that I'm building from the outside in, inside out, I guess. But my point is that the decisions for which word and which link action to use are independent of the process of building the tree. So on my first slide, I talked about building the trees from bottom up. And the C2A parser, the HPSG parser, they build trees from the bottom up. And they have to build all these branches. And the process of building those branches and deciding where branches should be attached, everything is very heavily tied to each other. Whereas here, the process of making the decisions is independent of building the tree. Okay.
Yeah, I have another question actually. So it sounds like what you described so far comes up with one tree or one parse per sentence. Have you considered yet cases where you actually might want more than one? So for like attachment ambiguity?
Thank you. That leads into my next slide. Okay. So he was asking what are you going to want to have more than one tree? So all of the parsers I have built so far, I haven't dealt with ambiguity other than just picking one and going on. And in that sense, there is no chart. There is no list of these are the things I've tried so far, and as we get on to the next one, should we try this or this, to do all the combinations. And that's what makes it so efficient, because I am not making more than one choice per word, essentially. Certainly you could do that, and I'd be open to helping somebody learn how to do this if they wanted to try that. So here, I've taken a word out of the sentence. Makes equipment with diesel and gas turbines. The word with can be attached to equipment, or the word with can be attached to makes. The equipment ends up with diesel and gas turbines, or Stewart and Stevenson uses gas and diesel engines to power the process of making equipment. Okay, so you can have, it can be attached either way. If you walk up to this sentence without knowing anything about Stewart and Stevenson and not knowing anything about gasoline, diesel engines, and equipment, you can't know which attachment it is just from this sentence. You cannot know. You won't find out just by looking at the sentence. You have to have something outside of the process, outside of the sentence, either the sentence that comes afterwards, the sentence that came before, or you have some background knowledge about Stewart and Stevenson, whatever. You have to have some outside knowledge. So in that case, the parser just has to pick one. You have to give up and just pick one. Unless you have some kind of stochastic, some other knowledge base that you can use to extend the parse. If you're working just from this sentence, you can't do anything other than just pick one. Now there are cases when you get to the end of a phrase and one of the words in the phrase is the clue as to how it should be attached. Classic one is he ate the cake with the spoon versus he ate the cake with the frosting. With is attached in two different cases, in two different words in both of those cases. And you get to the last word, spoon or frosting, and that's the clue as to where it should be attached to.
But it still relies on world knowledge, so it's not purely in the tree.
It's not purely in the tree, you're right. It does rely on world knowledge, thank you. But in that case, if you have a little bit of knowledge about eating and utensils, you can make the distinction. So in that case, and I'm sure there are other cases, you've all probably heard about garden paths. There are cases where the parser can know if it just waits long enough. And that's where the bottom-up trees, bottom-up parsers can beat this, because they can get to the end of that and they say, oh, look, that means it has to be attached here. And I've ignored those cases and found that I get pretty good results. Okay, I promised some experimental data. These are unpublished results I've sent for reviews and been rejected, so it hasn't been accepted yet. And also, Emily asked if I was going to publish the sources so that somebody else could share in how this works. And I will get around to that eventually, I just haven't done that yet. So starting at the top, a baseline append. If you think of that link action append, remember it was creating just a flat node. If you do that for all of the words in a sentence, you get 10% accuracy. This is unlabeled bracketing F measure, which means you compare this tree to the original tree from the test tree bank. If you do a baseline with an insert below on every word, so you get a right branching tree structure, and you get considerably better, but still not very good. 30. These are my 3 parsers that are best results so far. A naive discrete parser, which means for each word, those 2 decisions that you have to make, the target word and the link action, just pick the first one that is available for that word. So you find a word that you can target, and you find a link action that you can use for that pair of part-of-speech tags. And when you do that, here I was getting 53% accuracy. That's not a very good result. A CKY parser without anything else, just doing really minimal stuff, will get into the 60s easily. But on top of that, I added a maximum entropy classifier. What I mean by that is when I get to those 2 decisions for choosing the target word and choosing the link action, I use maximum entropy learner to decide on which one to go. And that improved the accuracy quite a bit, 82%. This is my best result in terms of accuracy so far. And then the thing I'm working on right now is what I call minimal unification. It's not HPSG unification. There's not all of the various fields that you have. And I'm just using a very small number of strings to use for unification. And I'm writing handwritten rules for this part. This is where I'm at right now, 69%. As I'm thinking I'm halfway through the rule set. I might be, it might be a third of the way through or a quarter of the way through, whatever. You never know until you get to the end. So I'm hoping that I can get up in the 80% range with that. Okay, so I need to do some comparisons. These are not necessarily apples to apples comparison. This Rourke parser from 2012, they were trying to improve the efficiency of several different parsers, and this was one of the results from that paper. I picked it out of that paper because it was the fastest one in the paper, 188 words a second, as opposed to many thousands of words per second in my parser. But the accuracy that they're achieving is much better. And if you've read much literature on parser, the really good parsers get up to 90–91%. And this is as close as a comparison as I can get in terms of comparing my parser to other parsers.
So this is all testing on Penn Tree Bank?
Penn Tree Bank, yes, thank you.
Isn't it the case that the best parsers get 90 or 91 labeled bracketing?
That could be, yeah. Yep. The question was, do the best parsers get 90–91% labeled bracketing? Yeah, I think you could be right.
So Spencer asked what kinds of features you use in the Maxent model.
What kinds of features did I use in the Maxent model? Mostly it was just the words before and after each possible attachment, and the parts of speech tags for all of the words in the range and so forth. So very typical features. And then the last line here is a dependency parser. The dependency parsers seem to be quite a bit faster, and I haven't really figured that out yet, except that they don't have to make quite as many decisions as the CKY parsers. This is definitely not apples to apples. This is more like apples to watermelon comparison. or apples to giraffes comparison. 91% attachment accuracy, and I believe that's a labeled attachment accuracy as well. But again, I'm just trying to show, that, one person looking at this parser for 2 years, I've achieved 82%, and these other things have had many people looking at them for many years, and the numbers have gradually grown. So I believe there are some possibilities here. So the two main things I'm really excited about Simple-Links for. One is the efficiency, the speed that you see here for these parsers. If you think of Twitter gets 500 million tweets per day, which works out to be about 140,000 words per second. So one core on a computer could handle that thing with this parser. And to me, that's amazing. If I could get somebody from Twitter to hear me say that, I think I could get some attention. We'll see. The other thing that makes me excited is on the next slide, but I'm not going to go to the next slide until I ask if there's any more questions on everything so far.
So my main question with all of this is, what can you do with unlabeled Pentry Bank style constituency trees? What does that representation get you? Okay, so the question is, what can you get with unlabeled trees? And the answer is probably not a whole lot. There are ways to get labels out of this, and I'm just ignoring that for right now. Right now, I'm going for bracketing accuracy and speed. And I've shown to myself that I can get labels out of it, and eventually there will be labels in the process. Do you expect the labels will slow things down? Maybe. And I also think that labeled Pentry Bank style trees are only minimally useful compared to what we can do with the more elaborate grammars. Okay, so I invite somebody to come and put unification on top of it, and then you can get almost as much data as you're getting from HBSG out of it. I'd be surprised because the structures are very different. Yeah, the structures are very different.
Well, for both of you, I would point to Gisle Yttersol's PhD dissertation from a couple of years ago in Norway, where he did work not identical to this, certainly, but using HBSG grammars with a sort of a transition-based deterministic parsing strategy to see how far you could get with that. And he did a lot of experiments in that direction.
Yeah, can you send me a link to that?
Sure.
Okay, so the comment was here about somebody in Denmark?
Norway.
Norway, thank you. That has something that might be similar to this using HBSG. I'd like to look at that, and I'll comment. Spencer asks an error analysis question. Do you notice any patterns in what sort of sentences do poorly in each of your systems? So the question is, are there sentences that do poorly, sentence patterns? So there are lots of things that I've had trouble with. The Pentry Bank has lots of sentences like, the sky is falling, said Chicken Little. And the last verb, said, has to be attached clear across everything else to the beginning of the sentence. And this is what has convinced me to try manually written rules, because I believe I can get past that problem. Right now, when the parser, these other three examples, the first two examples, sorry, when they get to that word said, they attach it to whatever's really close. And I want to get past that.
When you have other example or something, when you get to something that's, say, unlikely, when you get the full parse, do you have some confidence of after that?
So the question is, when I finish a parse, do I have any confidence as to how good the parse is? And right now, I'm not doing anything in terms of confidence for the entire parse. There are certainly things in the Maxent model that could be collected as you go along, and then you could do some combination of all of those decisions you've made as you go along. But I haven't done it. Okay, so I promised some speculation. This book, if you get nothing else out of today, go read this book. This is a great book. If you haven't heard about it, you need to read this book. Derek Bickerton is a linguist. He teaches it, or he used to teach at the University of Hawaii. He's a scientist. He has studied evolutionary theory. I happened to find this book. I was wandering around downtown Portland on a day off for myself. Went into Powell's Books, found this book, brought it home, and it's very good reading. He's somewhat irreverent. He's entertaining. It'll get your attention. I was turning pages as fast as I could. It's very good reading. So for this discussion today, there are two things relevant from his book. The first is that evolution uses very small changes to affect us, to get us to change. You make one small tweak in a gene, and you put that inside a creature, and if that creature is able to survive longer and create more offspring, then that gene gets to go forward. If that tweak in that gene makes the creature less likely to create offspring and go forward, then that gene is thrown away, that tweak is thrown away. So that's the way evolution works. So he is talking about, well, how did humans come to be able to speak, from the monkeys? Exactly, How did monkeys turn into us? And he's asking, we've got this fabulous machine in here. It is really such a fabulous machine that we have in our heads. How did it get there? One step at a time. You only get to tweak one gene at a time. And, it just doesn't happen overnight. And he asks those questions, and he comes up with a really good hypothesis that explains how it could have happened. It's just a guess. But it's a very good guess. And the process of describing all this stuff as it goes along makes it very entertaining and very eye-opening. So that's why I recommend it. But he says before we got to the point where we have syntax, that we're working with strings of words. You have 2 or 3 words together. There's no syntax, there's no order dependence or anything. So you take the 2 or 3 words and you change the order, and it doesn't change the meaning. And then somehow, all of a sudden, they started to put structure in there. And in the book, he talks about bottom-up parsing. And I said to myself, hey, I've got this thing. Look at this. We don't need bottom-up parsing. Look, this is much easier to do. You have this long line of words, and you just put simple links on top of that. And all of a sudden, you don't have to do bottom-up parsing. You don't have to have, 100 different genes coming together to make all this thing come together. You just need this one little tweak. And, I'm asking the question. I have no qualifications whether or not, this actually happened or if it's possible. I'm certainly not a neurologist. I have spent very little time studying evolution, but I think this is a possibility. And this is the other thing that gets me really excited about this thing, is that maybe this explains what's in our head. Maybe. Who knows? I'm going to do my best to tell everybody, hey, look at this. Okay, so thank you. Are there any more questions?
All right, well, thank you very much.
Thank you.